Kia ora and welcome to the first of 5 short webinars this week. David Pairman will set the scene for the remainder of the series with an introduction and update on our remote sensing science and how this informs the classification of our landscape. David has worked in the remote sensing field for over 40 years, leading research and the development of key New Zealand datasets such as the Land Cover database. I'll be back for Q&A at the end of David's talk, but now it's over to you, David.
Good morning. I'm David Pairman, and I'm going to be giving a very basic introduction to remote sensing concepts. I gave this talk last year, and so it's pretty much the same thing as I gave last year, but I have changed around a little bit at the far end, and hopefully it sets the scene for other talks in the short seminar series this week. So first of all, remote sensing, it's been around for many decades now, but over the past 10 to 15 years, it's really transformed from just providing stunning imagery, exciting images, through to actually providing a lot of operational techniques. So nowadays, instead of just looking at images, we're actually producing ways of generating maps that monitor our environment and underpin productive use of our land. So this transformation has been brought about by an explosion in the platforms in particular, satellites and drones, for instance, but also the instrumentation's got a lot cheaper, smaller, easier to launch, and the computing has got much more powerful. And of course, the analysis techniques supported by that more powerful computing have got more sophisticated. So this makes remote sensing a lot more practical and affordable, and is now routinely used in a lot of real ways, not just in a research sense. So this talk I've outlined here, I'll be going through a few basic concepts and whatnot, and then start talking about the instrumentation platforms and a little bit more about classification towards the end. So first of all, a definition for remote sensing. It's all about acquiring information about an object or surface without physical contact. So it's really interpreting electromagnetic radiation from the surface, and this can either be reflected radiation, which is ultraviolet, visible, or infrared, for instance, coming from the sun and reflected, or it could be emitted radiation, which is really thermal or gamma or microwave radiation from the surface that's directly emitted from that surface, or it could be backscattered from the instrument itself, where the instrument sends out active radiation and that gets reflected or backscattered in some way. I'll be covering a bit more about this later. The first thing I really want to talk about is resolution, which is a key concept in remote sensing. And there are 3 types of resolution. First of all, spatial resolution. It could be high, medium, or low resolution, and it's often a trade-off between the data processing costs and processing time as against what you're able to pick out. But I should point out that it's not really just that trade-off. You also want to be matching your applications to the resolution that you require. So for instance, we have here an AVHRR image, which is kilometre type resolutions, and that's very good for looking at weather over large scales or regional scale changes such as droughts. Whereas if you were looking at individual paddocks, you would want higher resolution data, and this is spot resolution, 5 to 10 metres, similar to the Sentinel satellites. And it's good for paddock level analysis. But of course, you can get much higher resolution imagery, even from satellites. And once you're getting down below a metre or half a metre, you start seeing individual stock and tree crowns and that, which may be what you want to see, but it may also make it a lot more difficult to analyse. So if you were trying to analyse crops in a paddock, you may not want to see the individual plants. It may be better to look at a slightly lower resolution imagery and match up to your application in that way. The second type of resolution I want to talk about is spectral resolution, and this is really where we are looking at the number and placement of bands in the spectrum, the electromagnetic spectrum, and different targets react or respond differently throughout that spectrum. So taking some samples through the spectrum can give you an indication of what the targets are. And most multispectral imagery or sensors these days would have 3 to 15 bands available to them. And I'll be talking a wee bit about this later on. The third type of resolution I want to emphasize is temporal resolution. And this is how many times you can revisit a point on the ground using the same satellite or perhaps a series of satellites with very similar characteristics. So temporal resolution, high temporal resolution gives you the ability, obviously, to help avoid clouds if you're talking about optical imagery, but it also captures short-lived phenomena such as a flooding event or maybe an oil spill event. But what I think is really exciting about high temporal resolution is looking at phenology. This is the changes in plants throughout the year, and that's things like flowering or leaf on, leaf off, or senescence. And by tracking the appearance of these plants throughout the year, you can actually tell a lot about the targets and help classify the targets. So that's quite an exciting thing to have high temporal resolution available. I'll move on to talk about some of the technologies that we use in remote sensing, and starting off with optical, which is probably the most familiar to you. This is basically just photographs of the ground, but in remote sensing, we're often looking beyond the visible spectrum that you would see with your eyes. So we'll be looking out into the infrared or near infrared, and these are usually or often represented as false color images. Optical imagery gives us high resolutions, and it's used in probably the large majority of remote sensing applications. And at Manaaki Whenua, we're very focused on vegetation classification, ground cover change, and vegetation health, things that we often use optical imagery for. Here you can see the placement of the optical bands in 3 different satellites, the Sentinel series up the top here, Landsat 8 and Landsat 7 below them, and you can see that you've got a number of optical bands available in each of these satellite series, which are placed in the optical windows through the atmosphere and can help tell you a lot about the vegetation on the ground. Hyperspectral is really just an extension of what I've just spoken about, the optical imagery. And in the case of hyperspectral, instead of having just maybe 3 to 15 bands available, you would have literally hundreds of bands available. And these be very narrow bands, maybe 5 to 10 nanometers bandwidth. And the objective here is to give you a full spectrum of the response from the target over the full spectrum. It does actually require some differences in the way that you do the analysis. You tend to use the data as a spectral cube rather than looking at individual bands, and it allows you to do some unmixing of individual pixels that might have a combination of target types within them. There's a trade-off between the spectral resolution and the spatial resolution often on these instruments, so that's something to look at. But the uses are in geology, at least where you can see the ground, which often isn't the case in New Zealand, where mostly it's covered in vegetation, the rock or soil. But also in ecology, you can well separate different species, and there are plant health and also coastal water applications where perhaps you're looking at plankton blooms that are very useful in hyperspectral imagery. I'll move on now to talk about SAR imagery. This is an active sensor. Usually it's a single frequency, and it is sending out a pulse of energy from the satellite to a target on the ground, and looking at the backscattered energy, both the transmission and reception of this energy uses polarized energy, so you can tell things about the shape and the size of the scattering elements and the orientation. Moisture is very important, and also surface roughness. So although it's single frequency, because you've got these multi-polarizations, you can in fact colorize up the polarizations and have what in some ways similar to a color image representing different aspects of the target here. As you can see, two different radar images, one at C-band, which is about 5.5 centimeters, and one much longer wavelength at L-band, and they're showing different aspects of the target vegetation. The applications are usually biomass measurement, one of the big ones. Vegetation structure is very good for change. Because it sees through clouds, you get very regular coverage from radar, and so it's good for looking at change. And there's also some more specialized applications I've listed there. Final one I want to talk about is LiDAR, and this again is an optical instrument where we're sending out a pulse of energy, in this case light from laser light from the instrument, which will be aboard an aircraft or drone. And you're looking at the time of flight of that pulse of laser energy, time that it takes to hit the ground and reflect back to the instrument. Gives you an indication of how close the ground target is to the instrument. And from that, you can derive things like digital terrain models, a canopy height model, that is how high is the vegetation above ground level, and a digital surface model. And there's lots of applications that use these types of models, both in the construction and surveying industries, flood protection, but also forestry, archaeology, and another key thing is to use terrain data to correct other types of imagery. So basically taking out terrain distortions and producing orthophotos requires a very good or an accurate terrain model to do that. So this can come from LiDAR technology. I'll move on to talk about the platforms that we use in remote sensing, starting off with satellites, which is probably what we use mostly within Manaaki Whenua. So there's actually hundreds of remote sensing satellites operational these days, anything from free-to-air type data, which we get from satellites such as Sentinel, through to subscription or pay for image services, which are usually at the higher resolution end of the satellite gamut. One of the advantages of satellites is that it's very regular, large-scale coverage. The satellites themselves are not very cheap to launch, so they're usually well calibrated and well designed, which makes it a lot easier and cheaper to generate analysis-ready data from. So it's actually cheapest to use satellites, although they're not so cheap to launch. The disadvantages tend to be limited temporal resolution. They're limited by their orbits, and this can be mitigated somewhat by using a constellation of satellites, and that seems to be the trend these days. Aircraft, of course, have been used since the dawn of remote sensing. Aerial surveying is one of the early sort of aspects of remote sensing, and so aerial platforms can be anything from a small fixed-wing aircraft up to huge aircraft such as the DC-8 shown here, when it was flown from Christchurch back in 2000. Aircraft can carry the whole range of instrumentation, so everything optical, LiDAR, radar, hyperspectral, etc., and some more sophisticated or what's the word there? More specialized types of instrumentation. The advantages are higher resolution than you might get from satellites. You're flying closer to the ground, and you can tailor your deployment. So actually plan your flight lines, take it when you need it, at the times you need it. And you can also fly experimental instrumentation rather than, it's a lot cheaper to put it on an aircraft than actually design and launch a satellite. And this is the case with this DC-8. It was carrying experimental radar instrumentation. The disadvantages, though, are mainly that it's quite difficult to calibrate. You've got usually a lot of small images to piece together. They're looking out at wider angles on the Earth's surface, and they're just, in general, not such well-calibrated instrumentation as you would get from on board a spacecraft. I'll move on to talk about drones. These are very popular these days and can be anything from toys to sort of high-spec military-type drones. The advantages of frequent deployment over a limited area. So, for instance, you could cover a farm or a vineyard very easily from a drone. You can tailor your deployments, put it up multiple times, just look at what you actually want to look at, program the flight lines, and of course you get very high resolution because you're quite close to the ground. I guess the disadvantages are that small extent, and at least at the moment in New Zealand, you're limited to a visual line of sight at this stage. So that may change over the next few decades. So now I want to look at what we need to do to make our data, once we've captured it from an instrument, make it analysis ready. And this really comes down to really pre-processing steps to allow images taken at different times or even from different instruments to be directly compared. So we're doing things like, first of all, the calibration for the instrument. There's often an atmospheric calibration needs to be done because the atmosphere may change over time, have different amounts of moisture in the atmosphere or aerosols in the atmosphere. So there are corrections that need to be made there. There's also the terrain and terrain distortions and projections, corrections that we need to make to get things onto a map grid, which is normally how we do the analysis, particularly when you're comparing imagery from different sources. You want it on some sort of common map projection. And then there's standardization of radiometric terrain effects, and this happens both in optical and radar imagery. And here we can see an optical case on the right-hand side. You can see some variation within these red patches, which is really to do with the vegetation on the ground, and it's much clearer than looking here on the left-hand side, where it's really masked by the terrain effects themselves, the slope and aspect. So if you can model out those things, it makes it a lot easier to do subsequent analysis and classification. So doing these pre-preparations allows our data to be analysis ready, and then we go into some sort of analysis technique. And the one I want to talk about today is classification. The aim of a classification is really to identify the membership of pixels or objects into a set of classes. So these would be some sort of set of classes that you've predefined that cover what your application is trying to look at. So it might be a whole set of crops, for instance, I've shown here on the ground, or it could be land uses, or things like the LCDB, which are sort of broader scale, not so much crops, but broader scale land covers. So you would define a number of classes, and the objective is to classify each pixel or object into those classes. We do this by giving the classifier a set of input features, and it's usually a data-driven approach. So it could be simple statistical models, or it could be quite complex machine learning or deep learning models that we use to do this. But the training data is required in these data-driven approaches, and that is key. And I'll try and cover that in a bit more in the next few slides. So the input features are what a decision is made from. Often in remote sensing, you might just present the classifier with the sensed bands as input features. However, it's possible to make band combinations and use these instead, or even as well as. So for instance, you could work out the normalized difference vegetation index, which is a near infrared minus red divided by the sum of the two, and that's a good index, or index widely used to differentiate between green vegetation and bare ground or dead vegetation. You can do a similar thing with temporal sequences. You might be able to summarize the temporal data into a temporal index that could be look at annual phenology rather than just presenting the classifier with every single individual image. And so why would you want to do this, summarize the data into less bands? Well, it really comes down to a bit of a trade-off in classification. You've got both your model complexity and your number of input bands or input features, and they're somewhat related. More complex models allow the classifier to see a wider variety of target patterns or characteristics, so they're more capable, but they might need more input data to do that. And conversely, if you've got more input data, that almost implies a more complex model. However, both an increase in the model complexity and the amount of input data does imply that you need a larger amount of training data to support it. So you're basically trying to parameterize the model, that's the underlying model, and you need, if you've got a more complex model, you need more training data to adequately parameterize it. So that's why you might try and reduce or summarize some of the bands and simplify it a little bit, because that can often produce a more robust result than just throwing every single bit of data at the classifier. So a couple of pitfalls I want to cover. As I've said, the training is critical in data-driven models, and one of the pitfalls is overfitting. So for instance, let's say we're trying to train a linear model. There's an underlying linear model that we want to train, and so we put a straight line through a number of data points, and you can see the data points will be not exactly on that line because there'll be noise inherently in that data. But let's say we actually had less points. Well, we could probably still see that we can fit a reasonable straight line through those few points if we didn't have as much training data. But if we allow the model to be more complex, then the model can overfit to the data, and it may actually fit a curve, for instance here, that is not actually appropriate for what the reality is on the ground. It can overfit that data, and the only way to really get around that is to go back to using more data or more training points to properly parameterize the model. Another pitfall is having an unrepresentative training set. So you need to make sure that the points that you choose for training cover the full extent of the relevant input feature space. So for each class that you're looking at, you might expect a range of ground training points to be appropriate. But if you just choose the very most pure or most pure examples of that particular class, then you can risk not being representative. What you really want is to choose a set of training that is representative of the full set that you would expect to classify into that class. So if you don't just want to choose the very best examples, but really look at what all of those that you would expect to fit into that class. More training is nearly always beneficial, with the proviso about being representative that I've just made above. So how do we go about testing and accuracy assessment? Well, for simple statistical models, the performance can be estimated from the training data, and assuming an underlying model and seeing how well that training data fits it. But that's not possible in more complex models such as deep learning, where it's often not even obvious what the criteria the decision has been made on. These tend to be a little bit of a black box where you have inputs and you have outputs, but quite how the algorithm works in the middle is actually not all that obvious. So what we do is we test it using independent data, and I must stress that it is independent. However, training data or testing data is usually a pretty scarce resource, and so you need to use a few tricks to try and maximize your use of that scarce resource. One of the tricks is to partition your data into a training and a testing set, and you can do that partition multiple times on the same set of data and run the analysis and get some idea of how much it varies from one run to the next. And that helps you identify where more training is needed. For instance, if you've got two classes that are not separating out well, you might need to add some training data for those two classes. And you can also experiment with the type of input data or the amount of input data that you require, and perhaps reduce some of the input data requirements or discard some input data that is particularly where it's correlated with other input data that you're already using. So it's very important to test the accuracy of your classifier, and key to this is using a lot of training data where possible. So I'm going to finish up there and open up for questions. Thank you very much.
Thanks, David. That was absolutely fantastic, and I think there are a good range of questions here. I'm just going to ask a couple of real quick ones because we've not got too much time for that. Rest assured, all the questions will be answered, and you'll be able to find that on our website. But one of the really pertinent questions is, how frequently does Landcare Research do land cover mapping on a nationwide basis?
On a nationwide basis, there's a couple of major projects like the Land Cover Database and the land use maps, NEMAFER's land use maps that are done at that sort of scale, and they're probably repeated every 5 years or so. We do a lot of other analysis for regional councils, and we have done some more specific analysis at looking at winter feed crops and that sort of thing on a national basis a number of times. So yeah, it just depends a wee bit of exactly what application you're looking at, but probably not every year, although some of these things are becoming quite practical to do every year.
Great. Hey, thanks for that, David. Look, 11 o'clock has rolled around all too quickly. Thanks everyone for joining us. You're now all set for the rest of the series. You'll understand what everybody's talking about. Tomorrow, James Shepherd will outline his work in overcoming the challenges of New Zealand's cloudy skies. If you haven't already registered for James or the following 4 webinars, do check the link that will be in the follow-up email to this one. and we'll see you tomorrow or later in the week. Many thanks. Mā te wā.
Thanks very much. Cheers.